So welcome to session 12 of Electrodynamics 2020. What I want to do today is cover the whole subject of special relativity and explain to you how it really directly relates to electrodynamics. So I just want to start with a bit of a revision of things that you've already done in the first year, basic aspects of special relativity that we'll be using as we go along. So quick reminder, what's the idea of special relativity? Well, Einstein had two postulates. The first postulate is that the whole of physics, all the laws of physics that you know, they don't depend on which inertial frame you're looking at them into. And an inertial frame is simply a frame, as you'll remember, that's not accelerated. The second postulate is kind of a very strange one when you think about it, but that's what it is. If you were to measure the speed of light in any of these inertial frames in vacuum, you would always get the same value. And that value we, of course, denote by c. Okay, so just a quick reminder of the consequences of that. Okay, we can play the classic game of considering a little train in which things are happening. So let's imagine we have a train wagon here, wonderful train wagon. And the person inside the train is going to do a couple of experiments. The first experiment is that the person in the train is going to measure the time it takes for a bit of light, say 1 photon, to go from the top to the bottom of the train. And we'll say that the height here is some given value h. So what's the time that this takes? So the delta t in the train for this thing is simply the height divided by the speed of light. Okay, that's the first experiment. But at the same time, on the ground, somebody's watching this train. And actually, as compared to the ground, the train is actually moving at a certain velocity v. Okay, that's going that way at a velocity v. So as far as the observer on the ground is concerned, when the little bit of light touches the bottom of the train, this event here, it occurs at a different place. Okay, so that would be the travel journey of the photon. But we've seen that postulate 2 says that the speed of light is the same in all inertial frames. And that means that the delta t on the ground, well, what is it? It's really distance traveled divided by c. But distance traveled is really h squared plus v times the delta t that you have. Okay, so that would be the square of that would be v delta t ground squared, and all of this in the square root. Okay, so what does that mean? Well, I mean, I can just replace h by c times delta t train here, and then I can just isolate delta t ground in this equation, or if you prefer, I'll just isolate delta t train. Okay, so delta t on the train is going to be, I'll just square this, put this on the other side, and then retake the square root. So that gives me a factor of 1 minus v squared over c squared times the delta t on the ground. Okay, so this is really the first strange things. So the clock on the train feels like it's running slow as compared to the clock on the ground, right? The delta t on the train is lesser than the delta t on the ground. Okay, so we can rewrite this equation in a more classic form. So delta t on the train is 1 over gamma times delta t on the ground, where this gamma, by definition, is 1 over 1 minus square root of 1 over square root of 1 minus v squared over c squared, is known as the time dilation factor. Okay, so that's the first strange thing about special relativity. Now, we can also do a second experiment. So second experiment. Now, what our friend on the train is going to do is put a mirror on one side. Mirror. Send a light pulse that will travel, hit the mirror, and come back, and measure the time that that takes. So let's say that the length of the train, as far as the train is concerned, it's called delta x train. So then the delta t in the train that you would have for the second thing would just be the distance traveled to delta x train divided by c. Okay, but on the ground, that's a train, I remind you. On the ground, something happens that looks quite different, right? Because you start here, and then there would be the launch of the light field, and then as the train would travel, at some point, there would be the event where the light, so here the light starts traveling, and then there would be a certain point at which the light has reached a point here, and let's say that, well, let's just define a few things. So first of all, here, that would be the length delta x as measured from the ground. And this event here, where the first one is measured, we would call that at time delta t ground for the first event. And then the train would carry on moving, and finally, at some point, the light photon would hit back its origin point. So that would be the second event that we would want. So from here to here, there's a delta t ground 1, and then from here to here, there would be a delta t ground 2 for the time it takes for the light field to back travel here. So what are these times here? Well, again, as far as the observer on the ground is concerned, the distance that the light will travel in here will be such that the delta t ground 1 is equal to what? So there's the delta x, of course, that needs to be traveled. But then there's also a v times the delta t ground 1, because that's the distance that the whole train has traveled. And all of that divided by c. Okay? So that means that the delta t ground 1 is just equal to delta x ground divided by c minus v. Okay, as if the light was traveling at speed c minus v, which it is in the observer's, in the ground observer's frame of reference. Now, similarly, you have that the delta t ground 2, which is the light coming back to its origin here, that's just going to be equal to delta x ground divided by c plus v, because now the light's traveling is in the other direction. All right, so where does that leave us? It means that the total delta t on the ground, which is the sum of the two, you can just add them up, right? So it's delta x times 2c over c squared minus v squared. Okay, which you can just rewrite if you want as this 2 delta x ground over c with 1 over 1 minus v squared over c squared. So this factor is just some gamma squared factor that we have there. Okay, now we had already that the delta t on the ground was equal to the gamma with delta t on the train, and this delta t on the train, was just equal to 2 times delta x on the train divided by c. So if I just put these two together, what it tells me is that the delta x on the train is going to be equal to gamma, the delta x on the ground. Okay, and that is called Lorentz contraction. Okay, so I'm sure you're already familiar with these concepts. So moving targets have clocks that run slow, and the moving object's length is Lorentz contracted. But that's the way you would just very simply compute these factors. Okay. Now, when we go from one frame of reference to the other, we want to have equations relating the various coordinate systems between them. And that's when we come to Lorentz transformations. So let's just recall very briefly how that goes with a very, very simple example. Okay, so what do I have? Let's say I have a first frame of reference like this. Okay, and this frame of reference will be called O. I'll use the same coordinate system as Griffith's, which is this like rotated from usual x, y, z like this. And now we imagine that we have a certain event in space-time here. Okay, so this is an event that occurs at a particular time, and in the frame of reference O corresponds to, so in O, it corresponds to a space-time point given by coordinates t, x, y, and z. Okay? Now, the idea would be to have another frame of reference okay, which we'll call O bar, in which the same event would occur at different coordinates, t bar, x bar, y bar, z bar. The question how we can relate these two. And what we assume is that the frame O bar is moving at a velocity v along x in frame O. All right, so let's just imagine what it is. So if we look, for example, at this axis, the x-axis along which the new reference frame is moving, the coordinate at which the event is occurring is going to be given by two distances. So let's assume so at t is equal to 0. The origins of O and O bar coincide. Okay? And now we will assume that the event occurs at a certain time t, which is greater than 0. So this distance here, yeah, the distance here is going to be v times t. So we can do a first relation. We can say that the coordinate x at which the event occurs is equal to v times t plus the coordinate d that we would have from the other reference frame. Okay, so d is the length in this new reference, it's the length in the reference frame of O that, you know, O thinks O bar would measure. It's the length that the event occurs at in O, but correcting for the VT of the other reference frame. So that would be the first relationship. So if we had Galilean physics, then of course what we would say is the clocks run the same. There's no difference, and we would say that the distance d that we have is just precisely the x bar that O bar would measure. Okay, so that would give us some very simple rules for transformation. It would just tell us that you know, t bar is equal to t. It would tell us that x bar is just equal to x minus vt, and y bar is equal to y, and z bar would be equal to y. But of course, there's a problem here because we forgot about Lorentz contraction. So we know that Lorentz contraction changes the actual measure that O uses as compared to that used by O bar. So really, the distance d that is measured by O as corresponding to the leftover measure above Vt that gives the x-coordinate of the event, it's not the same thing. We know that this length as measured in the O bar is going to be corrected by the Lorentz contraction factor. So that would be the relationship between the two. So really, that means that the x bar is going to be gamma times, if I then re-isolate d from this here, just x minus vt. Okay? Now, what we could do is just do precisely the same reasoning, but now from the point of view of the observer in O bar. So the observer in O bar, again, clock hits 0 at 0, just precisely as the clock in O. But now, in this frame here, this event occurs at a certain coordinate that would be, as far as O bar would be concerned, corresponding to a distance d bar plus the vt bar that you would have, and the v would be going the other way. So in the other point of view, so from point of view of O bar, we would have that this other distance would be such that the other coordinate would be related like this. Okay, precisely the same as here, but now as if the other frame was moving in the other direction. Okay, so change of sign of the velocity. But now again, invoking Lorentz, it's the same thing, but now the other way around. So we would have that the coordinate that would be seen in the original reference frame would have to be related by the factor gamma to the d bar that is like seen in the O bar frame. Okay, and that just tells us that x is equal to gamma with, now if I isolate d bar from this relationship here, just x bar plus vt bar. Okay, so now you see we have two equations relating the two pairs of coordinates like this. So we can solve, for example, for say t bar. Okay, so if I just look at this one here, so t bar would be equal to 1 over v with now 1 over gamma x minus x bar. Okay, so I can play with this if I want. I can say let me just use the fact that gamma squared is or let me first replace for x bar here, right? So I would get 1 over v, and now I have 1 over gamma x minus, then I'm going to use this relationship here, minus gamma x minus vt. Okay, now I can just say extract the factor of gamma, because that, so gamma over v with now 1 over gamma squared x minus x plus vt. Okay, and 1 over gamma squared is just 1 minus v squared over c squared. So you see that kind of simplifies things because the x disappears. So immediately that leaves for me just gamma times t minus then v over c squared, because there's 1 over v here, v over c squared x. Okay, so what we get with this are the Lorentz transformation rule. Of course, specifically for the case of travel along the x direction. So t bar is now gamma with t minus v over c squared x, and x bar is equal to gamma x minus vt. Okay, and of course the other coordinates are unchanged. Okay, so I'm sure you are already familiar with these rules, but it's just a very quick re-derivation to warm you up again for what's coming, if you needed that. Maybe one last comment. These rules here for the changes of one frame to another means that there's a velocity addition rule, which is again due to Einstein. And again, I'll leave it as an exercise to derive that. What you can do is just like do multiple frames of reference relative to each other, and then you just need to do one composition of this rule here. Say I have V13, which would be composed of the addition of V between 1 and 2, plus then a V between 2 and 3. Well, I would need to correct this by a factor of 1 plus V12, V13 over c squared. So irrespective of how much speed you add to something, how much velocity you add to something, you'll never be able to supersede the speed of light. Okay, so I'll leave the derivation of this as an exercise.